Hello everyone. In this paper, we propose an effective method on oriented and densely packed object detection. Object detection has achieved remarkable progress in several popular benchmarks, like Pascal VOC, COCO, where the objects are all axis aligned and locates relatively sparsely. However, the objects align along various directions and are densely packed in some scenes, such as in supermarket and aerial images. Detection in this area remains challenging because of the following three challenges. First, receptive fields of neurons are all axis aligned and of the same shape, whereas objects are usually of diverse shapes and align along various directions. Second, detection models are typically trained with generic knowledge and may not generalize well to handle specific objects at test time. Third, the limited dataset hinders the development on this task. Now, let's talk about the details of our proposed dynamic refinement network. The first challenge is that there is a misalignment between the receptive field axis aligned and of the same shape and the objects of diverse shapes and align along various direction. To alleviate the mismatches, we propose a feature selection module for dynamic receptive field adjustment. Specifically, we adopt a multi-branch structure. In each branch, we aggregate information using our proposed rotation convolution layer with different shape of kernels. Then, we fuse multiple information by spatial-wise attention mechanism. The proposed rotation convolution layer draws inspiration from deformable convolution network. Differently, we instead predict the rotation angle at each position and deduce the offsets of each kernel using rotation matrix. We provide a 3-branch case with 3 times 3, 5 times 1, and 1 times 5 kernels which are plotted with dotted meshes. The red solid rectangle represents the ground truth. Before rotation, the kernels are axis aligned and either cover multiple objects or can only cover part of the object. With the predicted angle, we rotate kernels accordingly. After rotation, we can see that the rotated 5 times 1 kernel matches the object best. The second challenge is due to the fact that most of the methods follow the stationary paradigm. We show a toy example of 3-class classification problem. The gray circular area represents the representation space and solid dots are examples that belong to 3 classes. Some samples are located far from the discrimination boundary, indicating that these data points possess good semantic discriminability. By contrast, the instances with small margin to the boundary are unfortunately not much compatible with the model. To enhance the flexibility of model, we resort to dynamic kernel mechanism. We obtain the F-triangle via a convolution between F-mid and the dynamic kernel. We treat the normalized F-triangle as the modification direction of F-mid. In this way, we can adaptively refine the basic feature according to its length. Also, we show an example of regression task. The orange solid dots represent the target values of examples, and the orange curve represents the learned regression model. We similarly predict an offset for each object to refine the regression results dynamically. The main difference is that we add H-triangle directly to HB to obtain the final regression result. In our experiments, we use CenterNet as our baseline structure, which models an object as a single point and regresses the object size and offset. To predict oriented instances, we add a branch to regress the orientation of the bounding boxes. We insert the feature selection module between the last convolution layer and the detection heads. To continue, we replace the conventional heads with our dynamic refinement heads, as shown in dotted rectangle. Moreover, we collect SKU110K-R to address the limited availability of related benchmarks. Our SKU110K-R dataset is an extended version of SKU110K. The orientation of images in original dataset are in a slight range. To enrich the dataset, we perform data augmentation using simple rotation. Then, we annotate the oriented bounding box for each instance via crowdsourcing. We verify the effectiveness of the proposed method with intensive experiments. We report our main results and show that our method achieves consistent and substantial gains compared with baseline approaches on DOTA, HRSC 2016, and SKU110K. There are some examples of detection results. We will to release the code and pre-trained models later. In the future, we plan to explore a more effective mechanism of dynamic models and investigate oriented object detection in other realistic settings, like weakly supervised or few-shot learning. Thank you for your time and attention.